Hello and welcome to Exploring Global Problems, a podcast where we talk to academics from Swansea University whose groundbreaking research is tackling global challenges, from health innovation to sustainable futures and the environment, from digital technologies to clean energy. My name is Sam Blaxland, and today I'm joined by Professor Gareth Jenkins, Associate Dean for Research, Innovation and Impact at Swansea. Gareth's research explores how DNA gets mutated and how that can increase cancer risks. He's the chair of the UK Government's Committee on Mutagenicity, the president of the UK Environmental Mutagen Society, and was recently elected president of the International Association for Environmental Mutagenesis and Genomics Societies. Gareth, welcome to Exploring Global Problems.
Thank you very much.
To start, can you just give us an overview of what your research and what all these long words that are very hard to pronounce is all about?
Yeah, so my research focuses on how DNA gets mutated and what the consequence for that is for human health, I suppose. A lot of this involves understanding how we can measure those mutations in DNA and then applying that to understand what the association between those mutations is and possibly human disease going forward, such as cancer.
Great. And you use blood to measure this in some ways, don't you, too?
Yeah, so I've had a long-standing interest in a type of esophageal cancer called esophageal adenocarcinoma. And for many years, we were interested in collecting tissue samples in conjunction with clinicians from the hospitals in the area, and then studying different things within the tissue samples. The problem with that is it's quite an invasive sort of procedure to get a biopsy from somebody during endoscopy. And so there's a lot of interest these days in moving to what are termed liquid biopsies. So actually using blood or urine or some other body fluid to understand some of the molecular changes like DNA mutations and how they might have a useful aspect to understand how esophageal cancer or any other kind of cancer or any other kind of disease may form.
Great. And I guess just from first principles, this is all very important because cancer affects so many people and you're trying to do what to change that?
Yeah, so I think recent figures have suggested that the cancer is going to affect 1 in 2 of us, so 50% of the population are going to get cancer at some stage. And I think the current aim is to try and detect it earlier, introduce new treatments and manage cancer. So people might be diagnosed with cancer, but they will live long lives, healthy lives, despite that, by having an earlier diagnosis and being open to then having more and more novel treatments that are going to be available in the future.
That's a huge figure, isn't it? That one in 2. I assume that encompasses some people who might die. I don't know, some of the older people who have prostate cancer when they die, etc. But I mean, the number of people who actually are very directly affected by this is still, like, in terms of percentage, it's massive.
Yeah, well, if you imagine, I think if you ask any of your listeners, then everybody knows people who have had cancer, have died from cancer, because it is so common, it's so widespread. Every time someone is diagnosed with cancer, it affects their whole family, all of their friends and communities. So it's a global problem for everybody because of the scale of the numbers of people who are getting cancer. And I think there are 2 types of people who are getting cancer. There are the people who are, quite elderly, they're diagnosed with cancer and there's some treatment available, but unfortunately there's very little that can be done, and those people will unfortunately die from those cancers. But there are plenty of people who are getting cancer at a younger age, in their 50s or even younger, and those people, if they had had a earlier diagnosis, could have probably had a better prognosis, because the opportunities to do something in terms of treatment, in terms of surgery, in terms of new therapies would have been there for them. But the late diagnosis was a huge problem for them. And so early diagnosis is probably the holy grail in cancer research. Yeah,
and I find that interesting because I'm a historian, so I think about it kind of historically. And, when the National Health Service was set up, for example, most people died of heart attacks and strokes. But now people are dying of kind of older people's diseases. But cancer isn't always affecting older people, is it? It can get younger people. And I suppose that must be one of the driving motives for you. It's not about people who are in their 90s necessarily who've had a very good life. It's about people who might be younger, and you can give them a better quality of life.
Yeah, no, I think cancer is unfortunately a problem of our own making, because we have been very successful at treating communicative diseases, so infections and other things. People used to die of all kinds of different infections before antibiotics were around. A lot of people died of cardiovascular disease 100 years ago. That is, there's still people who have cardiovascular disease, but it's better managed. And so every time you are saving people through advances in medical technology, you're allowing them to grow into older age. And unfortunately, cancer is sort of the thing that catches up with people in the end, because it's a disease mainly of old age. But there are plenty of people who get cancer in their middle ages. Yeah. And it's those people who probably with earlier detection could benefit enormously from having a longer lifespan.
Now, you talked about the challenges in detection, and how, in terms of how cancer is detected, how has that changed over time? Yeah,
so I think that there have been huge advances in imaging technologies and other kinds of technologies which have allowed us to detect cancer at an earlier stage. But it's often coupled to this biopsying, that you have to get you have to get a biopsy, because the gold standard way of detecting cancer is a bit of tissue sitting on a pathologist's microscope stage, and for the pathologist to say, yes, this is cancer. That's still the mainstay of detection. But there are modalities, new approaches around different imaging approaches, which are becoming more and more sophisticated. And there's a lot of molecular sort of research going on in terms of identifying things called biomarkers. So biomarker is a biological event, a change in a level of a biomolecule which is linked to a disease. And if you can obtain the necessary tissues and couple that to really accurate biomarkers, then that can be really useful in identifying early stage cancers, or even identifying pre-cancerous conditions which have got a high risk of them becoming cancer. This is detecting the step before cancer. I think this is where there's a lot of opportunity out there, that there are many types of cancer have a pre-cancerous stage, and a lot of people with that pre-cancerous condition won't develop cancer, but a small percentage will. And so if you can identify those small percent of the pre-cancerous diseases which are going to get cancer and intervene there by surgery or through closer follow-up with those patients, that could have a huge impact on cancer survival rates of individuals, and therefore at a population level as well.
Interesting. I was doing some reading about you and your work, and I mean, I know you specialise in esophageal cancer, and there was some talk about sort of acid reflux. And is that the kind of the area you're talking about here, that if someone is very acidic, then that might be a precursor to throat cancer or whatever? Yeah,
so there's actually a condition called Barrett's esophagus, which is formed by chronic reflux. So there's kind of a rule of 10% that if you have chronic heartburn, so acid reflux for decades, then there's a 10% chance on average that you will develop this Barrett's esophagus condition, which is a change in the esophageal tissue. The tissue actually adapts to that sort of harsh environment of acid reflux. But unfortunately, by adapting and changing the sort of structure, the architecture of the bottom of the esophagus, it puts it on a path for increased risk of esophageal cancer. And about 10% of people with Barrett's esophagus will get esophageal cancer then during their lifetime. So acid starts the process, it leads to this precancerous condition, Barrett's esophagus, and then about 10% of those go on to cancer. If we could understand who those 10% were, then NHS resources could be targeted to follow those people up, and the people who are less likely to get cancer wouldn't have to undergo invasive endoscopy, which is what happens every 2 years at the moment.
And I assume where in that case of the acid and the esophageal cancer, there's probably a similar kind of things for lots of other cancers as well that you could do investigations into.
Yeah, I think pretty much every cancer has a pre-cancerous condition. There's this term dysplasia that's used a lot, so it just means that there's abnormalities in the way the tissue is dividing and behaving, which a pathologist brands as dysplasia. And pretty much all cancers have this dysplastic pre-cancerous stage.
Just go back to first principles for a second. If there are people like me listening who aren't particularly scientific, I mean, how do people get cancer? What causes it?
Yeah, so that's a good question. I think that cancer is largely a disease of DNA mutations, which is why my fascination and many other people around the world's fascination with DNA mutation. So So the mutations occur during our lifetime, and they target particular genes which help control the growth of individual cells. And when those mutations happen to knock out those genes, to prevent those genes functioning, then that allows those cells to divide more rapidly. And the more rapidly they divide, the more likely they are to pick up another mutation, because rapidly dividing cells mutate more frequently. And so you accelerate the chance then of that becoming a bunch of cells, a clone, which can acquire all of the different hallmarks that are needed to become a full-on cancer.
Got it. And what things should people perhaps be avoiding if they don't want to increase their risk of cancer? I mean, we hear this word carcinogenic or carcinogens, but what are they and where do they come from?
Yeah, so cancer is caused by mutation. So anything which causes mutations will naturally be a carcinogen, will cause cancer. The only question is whether the exposure to that carcinogen is enough and over a sufficient period of time. So the types of carcinogens that are classically used to describe this are things like cigarette smoke. So cigarette smoke contains thousands of chemicals which have been dozens and dozens, if not hundreds, have been classified as individual carcinogens. So you're breathing in a cocktail of carcinogens every time you smoke a cigarette. And that increases enormously your risk of getting lung cancer and other cancers as well, because those carcinogens get into your body, so they can cause bladder cancer, liver cancer, and other cancers as well. Other carcinogens that are often used to describe this sort of process are things like UV light. So the more you sunbathe, UV light has a fantastic ability to cause DNA mutations. So the more you sunbathe, the longer you sunbathe for in terms of the number of years you do it for, the greater the chance that some of those mutations in your skin cells will actually cause skin cancer to arise.
Hence, so much more cases of skin cancer in Australia, for example.
Yeah, so I think in Australia, you've got a sort of Western European population who've moved out, particularly people who've emigrated from the UK, where we don't get a lot of sun, have moved to a country where there's 10 hours a day of really strong sunshine. And so there's been an increase in the rate of skin cancer in Australia. But I think that the more, one of the interests that I have is if we can understand these carcinogens more and we understand how they can cause those mutations and then increase risks of getting cancer, then we can do something about that in terms of prevention. So in Australia, they have I think it's called slip, slap, slop or something, the sort of public health mantra that everyone should be wearing sun cream, they should be covering up, they should be getting out of the sun in the sort of midday sort of periods. And that has come from the realization of what was causing the skin cancer. The smoking ban that was introduced 15, 20 years ago had a huge effect on reducing the number of people who were smoking. People have alternatives now to smoking. So I think public health can step in when there is the science to identify this thing can cause cancer. And if you reduce exposure to this thing, you will reduce your opportunities of developing cancer. And even further than that, there are plenty of things that we can do to reduce our risk of getting cancer. So there are, as well as carcinogenic compounds and carcinogenic exposures like UV light, there are things which protect us. They protect our DNA. And so we can reduce our risks of getting cancer by increasing those protective factors and reducing at the same time our risk, our exposure to the things which cause an increased risk of cancer. So those protective factors are things like fruits and vegetables, healthy diet, exercise, and many other things which are being understood now, better understood, that actually protect our cells from the DNA damage, which leads to the mutations, which leads to cancer.
I mean, you mentioned food there in the context of fruit and veg, but is there clear evidence that there's carcinogens found in particular foodstuffs as well?
Yeah, absolutely. So there are plenty of one of the chemicals which is in cigarette smoke, benzoapyrene, is one of the carcinogens that's often used as an example of a carcinogen in cigarette smoke. Actually, is present because it's formed by the by the burning process. So really char-grilled burnt meat can have benzopyrene present in it. It can also have chemicals called heterocyclic amines, which are another type of chemical formed by the burning process of meat. So heavily overcooked meat can contain these carcinogens, which can then increase risks of developing colorectal cancer. And there are other examples. We sometimes have contamination events in some foods which are contaminated with certain things. Not so much in Western Europe or in the West in general, but there are contamination events that occur in the developing countries, which can produce chemical exposures and increase risks of certain compounds because the food quality isn't perhaps as assessed quite as much.
And this is going to be my next question because we've spoken a little bit about Western countries and obviously mentioned Australia, but you actually work quite a lot with low or middle income countries, don't you? Or that's your focus of your research.
So we've started a collaboration with Bangladesh to begin with, and this has been partly because of links between clinicians, doctors here in Swansea who trained in Bangladesh and have established a charity to go back to Bangladesh and train Bangladeshi doctors in the latest medical procedures that can help treat patients there, because I think that they have a lot of the infrastructure and facilities for these advanced sort of processes, but they lack some of the training sometimes because they aren't fortunate enough to have something like the NHS. So we've been doing some work with Bangladesh trying to understand if we could help with understanding the exposures of the Bangladeshi population to certain types of carcinogen. And in Bangladesh, they have a particular problem because you often hear on the news about the flooding, the monsoons, which affect Bangladesh. It's a very water-based country. There's lots of wide river deltas. And unfortunately, the river water, the water in Bangladesh has got a high level of contamination with arsenic. And arsenic comes up from under the soil. The water leaches it out of the surrounding soil, particularly during the flooding sort of periods. And arsenic, we always think of arsenic as being the classic poison used in an Agatha Christie movie. Mm-hmm. But as well as being a poison, it is a really potent carcinogen, and exposure to arsenic for a long period of time can increase your risks of getting cancer. And so there's a lot of efforts trying to be started to try and understand how the arsenic exposure in rural parts of Bangladesh is linked to the growing rate of cancer. So in Bangladesh, the average age of people getting cancer is in their 40s. It's much, much younger than you would imagine in the Western world. And this is probably due to the fact that they have these contamination events. And it's probably underreported as well because they don't have, in the rural parts of Bangladesh, the reporting structures, the sort of the equivalent to the NHS to record every death that happens and the cause of every death.
Yeah. I was about to say this research must be fraught with challenges. I mean, just methodological challenges, but also things that are quite difficult to grapple and deal with just kind of psychologically as well.
Yeah, no, there are huge challenges to doing this kind of work. But I think it's really valuable for us in the West to try to do something to help countries that are in this LMIC, the low middle income country bracket, that they don't have the facilities to be able to do some of the work. They don't have funding to fund lots of the investigations, to understand their exposures, to help their citizens. And so I think it's beholden on the richer Western countries, including the UK, to do something about this. And we did have the Global Challenges Research Fund, which the UK government introduced particularly for this purpose. Unfortunately, that was pulled a few years ago. But before that happened, we were able to get some money from the Global Challenges Research Fund to buy some equipment for the Dhaka Medical School, the Dhaka Medical College in Dhaka, the capital of Bangladesh, to try and introduce some facilities so they could start building up some research capability to look at some of these things through measuring DNA damage, DNA mutations that were induced perhaps in relation to arsenic. Unfortunately, the second part of that, the training element where we were going to ship 6 clinicians from Dakar over to Swansea to learn sort of from us some of the approaches that they could apply. Got hit by COVID, and unfortunately they were unable to travel. So we've been sending them some information instead, which is okay, but it's not quite the same thing as them actually getting their hands dirty, learning something in our labs here at Swansea University.
In person's often better, almost always better. Yeah. Do you ever get critiqued by people? You know, you said that it's good for first world countries, Western countries, to go and help people who are less well off. But do you ever get criticised for that by saying, well, we still have big problems kind of medically in the field of cancer here, and we should be putting our energies in British universities into the domestic kind of market, I guess.
Yeah, I guess if we were focusing all our efforts on helping an overseas country tackle a particular challenge, then that may be a criticism that was valid. I'm not sure that would be valid. I think that you have to do something where the need is greatest often. But I think in reality, lots of people at Swansea University and at other universities in the UK have links with lots of different third world countries, developing countries, countries on the LMIC, the low middle income country list. And I think the intention of all that is very noble, and it is about upskilling and helping the people in the overseas country to train their staff, to train their students so that they can solve their own problems in time, and by collaborating with countries in the UK and understanding some of the approaches that they can take and how they might deploy those in their local context is not taking away from tackling the fundamental problem, which would be of relevance to the UK population.
Well, yeah, I was about to say, people often will say in response to that critique is that you're still learning stuff when you go to these other places that can be deployed back at home as well.
Oh, absolutely. I think that a bit like medical students who go and do elective courses where they go to overseas countries and spend a couple of months working in a hospital somewhere. They see things in those overseas countries that they wouldn't see in a normal hospital here in the UK, and by doing that, they get huge broadening of their experience, and it's a benefit two ways. It's a benefit from that collaborative link to the sort of Western European countries' medical sort of training facility, but it's a benefit to those individual medical students because they get to learn about things that they would never usually see in their day-to-day job.
Let's just talk about a bit more about you specifically, Gareth. You've got an impressive CV. I think it's fair to say you've got all these organisations that you're part of with these long words that it only took me one take, of course, to say in the opening of this episode. But I mean, tell me a bit more about what you're involved in, how it's sort of given you a new perspective and changed the way you work.
Yeah, so I think that in the last 3 or 4 years, I've taken on some sort of senior roles, I suppose. But I think this has been part of my career has been about getting involved in organisations. So I've been members of different organisations previously, and in the last few years, I've got to that position now where I've taken on being president of a few societies. One of them is a UK-based DNA mutation society, the UK Environmental Mutagen Society. I was a member of the UK government's Committee on Mutagenicity. 10 years ago, I joined that committee and then rotated off. And then 2 years ago, I applied to be the chair. There was a vacancy for the chair of that committee, and I took on that role. And that's quite an important role because it advises UK government departments on the risks to the UK population from exposures to things such as food contaminants and other carcinogenic and mutagenic threats, so chemicals which can cause cancer or DNA mutation. So these things have happened through, I guess it's like an apprenticeship sort of system that I became members of those organisations when I was younger, when I was before I became a professor here at Swansea University, and then through continuing activity and engaging with those, I've now got to the point where they've asked me to take on being either president or to chair those committees.
Is it strange now being in a leadership role and you look back and think, I was just a humble mere member a little while ago? But it's often when you get to the top, it doesn't feel as overwhelming as it might have looked when you were a junior person on the committee. It's a strange feeling, isn't it? Yeah,
it is strange. I think that when you're an academic, you're encouraged. When you're a junior academic, you're encouraged to network. It's one piece of advice I always give to people is to get out there and get yourself known, get yourself involved in lots of organisations, committees, scientific societies, other government bodies, whatever is appropriate to your field. And being a member is great because it gives you the experience of understanding how these things work. And so you do your apprenticeship by spending time working in that organisation, working on that committee. And then when the vacancy comes up to chair or to become president of those societies, then as I've done recently, taking on those roles, I've actually looked back and exactly as you just said, thought that 10 years ago when I was applying to be a member of those and looking up to the person who was the president of the organisation or was chairing the committee, thinking, wow, they must have really sort of be well respected in their field because they're in that kind of role. And so to think that I'm in that role now is a little bit humbling, I think.
Yeah. And you were appointed to the Committee on Mutagenicity by a certain man who's been on the front page of my Daily Telegraph at the beginning of this year a little bit. I do read other papers, of course, but the Secretary of State, the then Secretary of State for Health, I assume, Matt Hancock.
Yeah. So I've actually got the letter of appointment on my wall. Not because of the controversy that came later, but the letter with the government sort of headed paper, and then his signature signing the letter inviting me to become the chair of the Committee on Mutagenicity was quite a big event for me, quite a big event in my career. Unfortunately, I think it was a month after that he was forced to step down because of COVID breaches, and we've heard all of the things that have happened as well around that recently.
I mean, with these committees, obviously I have to be quite brief here, but firstly, why are they set up in the first place? And in your role, what are you doing on them? Because obviously it can't be a full-time job because you also work here and you've got like management roles here. So yeah, what are they for and what do you do?
Yeah, so the Committee on Mutagenicity that I chair is one of 3 committees which advise government on the safety of chemicals which we as UK citizens may come into contact with. So the other 2 committees are the Committee on Toxicity, and there's a Committee on Carcinogenicity, which I also sit on as a member because of my role of chairing the COM committee. And so what we meet, so the COM committee meets 3 times a year. We have day-long meetings where we go through a packed agenda dealing with different issues and offering an opinion, which then goes to UK government departments who then enact what they think is the right thing to do. And so some of the things that we might get asked about would be things like a chemical or an agent which has been identified as potentially a risk to human health. So one of the things that we're dealing with at the moment that I think I'm okay to talk about is the issue of titanium dioxide. So titanium dioxide has been in foodstuffs and in sunscreen. So people who wear the bright blue sunscreen they put on their nose and other things, there's a lot of titanium dioxide in there, which is very good. It's a very good UV absorber. But there's been suggestion that titanium dioxide, if we were to ingest it, could be a carcinogen. It can induce DNA mutations and it could be carcinogenic. And this has been raised as an issue by the European Food Safety Authority, EFSA, who last year introduced a ban on titanium dioxide for foodstuffs. Now, there is a bit of controversy around this, and so in the COM committee that I chair, we're actually looking at the evidence to try and review the evidence ourselves to come up with our position so that we can inform UK government what we think the situation is with titanium dioxide and whether there should be any kind of restriction on its use.
Great. That's one nice little case study there to get some sort of idea about what it involves. But obviously it's a lot of work, a lot of extra work.
Yeah, no, it's a huge amount of work. So I mentioned that the COM committee meet 3 times a year. in between those 3 meetings, in the last 12 months, we've had 3 separate meetings which have just been focused on titanium dioxide. And we are in the middle of doing a review now, which is going to take a number of the members' time over the next couple of months. I should point out that the B word comes into this a little bit. So there is an impact here on Brexit, because previously the ruling from the decision by the European Food Safety Authority would have applied to the whole of the EU, including the UK. But because of Brexit, there is the opportunity, I guess, for the UK to look at this independently and to come to its own decision. So Brexit has increased the workload a little bit of these UK government advisory committees, because they now have to, maybe it's just to ratify a European decision. And often it is the case, because in the EU they have committees which are made up of expert members, and they make really good decisions, well-informed decisions. And so often in the UK the equivalent structures are just ratifying what the EU committees have already said. But in some cases there is a difference of opinion, and so there is the opportunity to sort of diverge a little bit. But it does mean everything has to be revisited on a UK basis, and there's a lot of uncertainty around how this happens in practice, because these new rules only came in January, I think, of 2021, and so we're only a year or 2 into this new regime where we're having to revisit some of these things that have previously been done by the European Union's organisations.
So being nice and impartial here on the whole Brexit and European Union issue, you could say that that's giving opportunities for Britain to, in that sort of slogan, to take back control. But obviously it's also a lot of extra work, because it's just putting a lot more on the plates of people here.
Yeah, I think there are genuinely some opportunities. I think that in some case you could argue there's some unnecessary duplication, but there are opportunities. One of the opportunities that I think we could grasp would be that. So in a lot of the research that we do in Swansea, in the research group that I'm in, is to look for animal alternatives, because a lot of the testing of whether something is a carcinogen, whether it causes DNA mutations, is carried out in rodents, and they're not very good models for studying human mutation or human carcinogenicity, because we're not big mice. We're very different physiologically, anatomically, and so what we do a lot of here at Swansea University is develop alternative in vitro, so cell-based approaches to those sorts of questions. And one of the opportunities with the divergence from the EU around safety assessment of these kind of chemicals is that we could really accelerate that 3Rs, the sort of animal alternative agenda. And in the EU they're very keen to reduce animal testing as well. It was the European Union that introduced the cosmetics ban, so animals couldn't be used in testing cosmetics. That came from an EU directive. It took about 10-15 years to come into sort of being. So they want to drive this agenda around reduced animal testing, but we, as a consequence of Brexit, could even accelerate that faster if we chose to.
Go back to you in particular, and the way in which you got into this area of research. You told us before we started recording, actually, that you studied under somebody very interesting when you were an undergraduate, didn't you?
Yeah. So I did a biophysics degree at King's College London in the late 80s. And I was fortunate now, I didn't realise at the time, but looking back, I was fortunate that I was actually taught by Maurice Wilkins. So Maurice Wilkins is the third man of the double helix. He's the forgotten man. So people often talk about the identification of the structure of DNA, the double helix structure, that it was discovered by Watson and Crick. And it was Watson and Crick who wrote the paper, but they couldn't have done it without Maurice Wilkins and Rosalind Franklin, who were based at King's College London. And when they were awarded the Nobel Prize, it was Watson, Crick and Wilkins who got the Nobel Prize. Unfortunately, Rosalind Franklin had died before the Nobel Prize was awarded, and you can't get the Nobel Prize posthumously. So she missed out, even though she probably did most of the work, because she was actually the person who was generating lots of the data. Yeah, so Morris was a really interesting character. He worked on the Manhattan Project during the war, developing the atom bomb in America. He was a physicist, came back to the UK afterwards, and I think was affected by the atomic bombs that were dropped on Japan, and moved away from anything to do with atomic physics to looking at studying biomolecules, hence his interest in the DNA structure. And he started getting really interested in bioethics, understanding, not just how, whether we can do things, but whether we should do certain types of research. And it was a module on bioethics that he taught me on, and he was fascinating. He was probably 80 then when he was teaching in the sort of late 1980s. But fascinating man.
That's dedication. And when did you come to Swansea?
So I came to do a PhD here in the mid 1990s. I think it was 93. And I came here because there was someone based here at Swansea University called Professor Jim Parry, who was an international expert in the DNA mutation world. And so I saw an opportunity to apply for a PhD. I was working in Cardiff University at the time. And I jumped at the chance to come down and visit him and apply for this PhD. And I was lucky enough to be offered it. And I worked with him for 10 years or so until he retired. And he had an international profile in terms of being involved in lots of different aspects of understanding how DNA mutations were caused and the consequence of how we look at the risk that poses to the human population, which is something that I've continued, as well as a couple of colleagues of mine in the same research group. We all studied under him, and we're keeping his research ongoing. We're sort of building on his shoulders, I guess.
Great. Now, you might have mentioned this already, but genomics in general, I know you work on that. Can you just tell us what it is? Because I must say I don't have any idea really.
Yeah, so genomics mainly means sequencing of the human genome. So the Human Genome Project, which completed about 20 years ago, took about 10, 15 years with hundreds and hundreds of labs around the world trying to piece together the sequence of the 3 billion bases that are included in every cell of our bodies. And now genomics, because of technological advances, we can identify the genome of a human within days, if not weeks. So what took 10, 15 years previously now can be done in weeks. And so this is really powerful to be able to understand the origin of lots of different diseases, to understand the role of mutation, because obviously by studying the whole genome, you can identify where these mutations are arising, and you can describe them, you can quantify them. So genomics is a really powerful tool for understanding disease, and undoubtedly will be really important in terms of early cancer diagnosis in the future. But the main issue for it being deployed in some kind of diagnostic approach at the moment is it's still relatively expensive. That even though the costs have plummeted, so the Human Genome Project cost billions of pounds, and now a genome can be sequenced for thousands of pounds. So the costs have come down remarkably. But if you imagine that through our beloved NHS, if we tried to use genomics to look for early cancer in a screening kind of process, you'd bankrupt the NHS overnight, because it would cost trillions, if not whatever the one above trillions is, gazillions maybe. So it is enormously important technology that will revolutionize medicine in the future, and is starting to do so now in a targeted way. But it is still relatively costly to be rolled out at a population level. You
think it's going to be the gold standard in the future, don't you?
Yeah, I think so. I think in the future. I'm lots of the research that I do uses alternative approaches, and I'm kind of writing myself out of a job by saying that we won't need to do any of these things in the future, because genomics will come in and replace them when the costs become a little bit more achievable. And I think that they're already on the decline in the cost is remarkable over the past 15 years. And I think in 10 years' time, it will be used for all sorts of different purposes, and we will be regularly sequenced. I think the issue with thinking of this as just being the sort of the answer to everything is that we're born with a genome which starts mutating the day after we're born. So every cell in our bodies is mutating every second of every day. We're picking up mutations. Most of them just mean nothing. They aren't in important regulatory parts of the genome, so they won't be noticed. They won't have any consequence at all. And it's only those occasional mutations that occur that could have a consequence. They could increase your risk of developing cancer, or they could change the function of a protein and give you another type of disease. So using genomics is fraught with some difficulty because our DNA is constantly evolving. It's not designed to stay the same.
With all this knowledge and understanding at your fingertips, and particularly with the stuff about carcinogens and knowing what causes cancer, do you still, regardless, sometimes do things or eat things or behave in certain ways that is probably, in inverted commas, not good for you, even though you've got all the info? Because I should say not from this university, but I've known kind of medical types who are heavy smokers, for example.
Yeah, no. So the answer is yes. But I think it's important to remember that our exposure to carcinogens is very much based on the dose, the actual level that we're exposed to. So, I wouldn't advocate smoking to anybody, but if someone smoked a cigarette one day, they don't increase their risk of getting lung cancer. That is a really, you have to be a smoker for 30, 40 years until you start to see the rise in the risks of lung cancer. We have lots of protective mechanisms in our bodies to help repair the damage that's done by exposure to carcinogens. And so it's that balance between the amount that you're exposed to and the time that you're exposed to that for against our protective mechanisms. And so if you have a barbecue and you eat barbecued food, I often do that. I don't think twice about it. It's not increasing my risk necessarily. If I ate barbecued food 3 times a day for 20 years,
you'd worry a bit.
I would be worried, yes. So I think that, definitely. I think it's all about moderation. That having exposure to things. Sunbathing. I like nothing more than going on holiday and having a walk around, and getting exposed to some nice warm sunshine in the Mediterranean.
You don't sit there worrying about it particularly.
I don't worry about it at all because I do use sunscreen. Having lost my hair when I was in my 30s, when I had children, I think that I regularly apply sunscreen to my head because I think I burn otherwise. But I'm more worried there about burning rather than getting skin cancer, because I think low dose exposures to even carcinogens is not something necessarily to worry about.
And I assume that the same principle applies then for drinking alcohol as well.
Yeah, so alcohol's an interesting. So alcohol. So when we drink alcohol, our livers metabolize alcohol into a compound called acetaldehyde, and acetaldehyde is a carcinogen. Alcohol isn't necessarily a carcinogen, but acetaldehyde is. But again, low dose exposure to alcohol and acetaldehyde doesn't really increase your risk. I really like the sort of scientific evidence which suggests that there are compounds in red wine, polyphenol compounds called resveratrol. And resveratrol is very good at reducing DNA damage. It reduces inflammation. It protects our cells. And so drinking red wine in particular, moderately, would actually, probably on balance, have a health benefit over a health risk. It's all about getting that balance right.
That is what I like to hear. Very much so. Listen, Gareth, there's lots of people who'll be listening to you and thinking this is really cool and important work. Particularly if they're young people and they want to maybe get into this line of work. What advice would you give them?
So I think that people who are already studying at university who are interested, I think that there are plenty of opportunities to look for courses which can teach you more about genomics, around aspects of how carcinogens work. I'm a geneticist by training, and so I think having a background in genetics is really useful for the cancer genetics sort of side of the research that I'm interested in. So I think that there are plenty of undergraduate degrees which focus on that. There's plenty of master's degrees for people who've done a first degree who want to maybe specialise a bit more. And of course, in science, we often are encouraged to carry out PhDs to really push home the sort of area, to become an expert in an area. And so there are plenty of universities around the world, but plenty in the UK who focus on things to do with cancer genetics, who are interested in studying carcinogens. And so looking out for opportunities to carry out a PhD would be good advice, I think I would give people.
It's been a really interesting conversation, Gareth, and I've learned a lot, so thank you very much. If you want to find out more about Gareth's research, you can visit his staff profile page on Swansea University's website. To find out more about this podcast and Swansea University's research, visit swansea.ac.uk/research. That's all from us today. Thank you for listening, and thank you once again to my guest, Professor Gareth Jenkins. If you've enjoyed this episode, please follow us. I'm Sam Blaxland, and that was Exploring Global Problems from Swansea University.